In today's lesson, we're going to be looking at exponents, and we're going to be doing a review of the exponent laws and simplifying powers, as well as exponential relationships. So some of the exponent laws that we want to review or deal with when we're trying to simplify powers are our multiplying, dividing, and power to a power laws. So if we're multiplying exponents with the same base, or powers with the same base, so x to the power of a times x to the power of b, again the same base of x, when I multiply them, I'm going to add my exponents. So it becomes x to the power of a plus b. And again, this only works for powers with the same base. So that x, it could be a variable or another letter, or it could be a number. As long as it's the same base and you're multiplying them, you can add the exponents. If we're dividing powers, so x to the power of a divided by x to the power of b, we subtract our exponents. So x to the power of a minus b. For a power to a power, so x to the power of a to the power of b, I multiply my exponents. And again, we have looked at other examples or more in-depth examples of this in previous lessons. The zero exponent, anything to the power of 0 is always 1. For the negative exponent, if I have x to the power of negative a, I usually want to convert this to a positive exponent, so I would flip this. In this case, x is a whole number, so it becomes 1 over x to the power of a. If I had a fraction, say x over y, to a negative exponent, I would flip my fraction, y over x, and then my exponent would become positive. So that's how we deal with positive or negative exponents. Exponential growth and exponential decay are almost virtually identical in terms of the equations. Exponential growth, y equals a 1 plus r to the power of x. A is the initial amount, and r is the growth rate as a decimal. So you will be saying like something grows at a rate of 5%. You have to turn that to a decimal. Exponential decay is very similar, except we are subtracting the r value. So in this case, the equation for exponential decay is y equals a 1 minus r to the power of x. A is still your initial amount, and r is your decay rate or rate of decay as a decimal. If we are writing exponential equations from a table of value or table of values, it's going to look very similar in the end. However, we are going to have a different general form. In this case, y equals a b to the power of x. A again is still the initial amount, and b is the ratio, and the ratio we get from our table of values. And it's similar to first differences. So first differences were where we subtracted the y values. The ratio is where we divide our consecutive y values. So bottom divided by the top, bottom divided by the top. And we will look at an example in this lesson of that as well. So moving on to some examples of simplifying the following. So I want to use my power laws to simplify the following. So 2k to the power of 3 times 2k to the power of 4. So because I'm multiplying, I can multiply my two numbers. So I can do 2 times 2, which is 4. And for k, because it's a power with the same base, I can simplify that by adding my exponents. So k to the power of 3 plus 4 equals 4k to the power of 7. For b, 3x squared times x to the power of 4. Again, 3 is on its own. There's no other number I can multiply it by. X squared times x to the power of 4. Because I'm multiplying powers, I can add my exponents. And again, they're all the same base of x, so that does work. So 3 times x to the power of 8. For C, 4 times 3 is 12. P squared times p to the power of 5 is 2 plus 5 equals 12p to the power of 7. For D, power to a power, so I have u to the power of 3 times v to the power of 5, all to the power of 2. I can't simplify the u and v because they're different bases. U is different from v, so I can't join them, but this exponent of 2 I can apply to both parts. So the power to a power rule states that it's the exponents multiplied. So 2 or 3 times 2 and 5 times 2. So this becomes u to the power of 6 times v to the power of 10. For E, again, same thing. I can't combine anything inside the bracket because they're all different bases. But the exponent of 4 on the outside I can apply to everything on the inside. 2 to the power of 4, y to the power of 5 to the power of 4, power to a power means I multiply my exponents. X doesn't show an exponent, but when we don't see an exponent, we say it's 1. So x to the power of 1 times 4. I can simplify some things. 2 to the power of 4 is 16. Y to the power of 20. And x to the power of 4. For F, it's the same thing. That 3 applies to both parts. 6 to the power of 3. Y to the power of 8 times 3, because it's a power to a power. Again, remember, when you're dealing with numbers and you're trying to simplify them, 6 to the power of 3 is 216, so it's 6 times 6 times 6. It's not 6 times 3. Remember, that exponent means the number times itself however many times the exponent tells us. And then we get y to the power of 24. For G, x to the power of 5 divided by x to the power of 2. So when we're dividing powers with the same base, we minus our exponents. So x to the power of 3. H, we're dealing with multiple variables, so we focus on what's similar. We focus on just the x's and just the y's. So x to the power of 7 divided by x to the power of 3, so 7 minus 3. Y to the power of 10 divided by y to the power of 5, or 10 minus 5. We get x to the power of 4 times y to the power of 5 as our final answer. For I, again, we have multiple terms here. We have numbers, we have n's, and we have m's. Again, we're going to focus on what's similar. 12 divided by 3 we can do, which is 4. N to the power of 5 divided by n to the power of 2. Our rule tells us to subtract our exponents. And for m, 4 minus, and again, we don't see anything, so we assume there's a 1, so 4 minus 1. So 4n to the power of 3, m to the power of 3 is our final answer. For J, 100 to the power of 0. This you could do on your calculator if you're not quite sure, but again, the 0 exponent rule tells us that anything to the power of 0 is 1. Even for the next one, we have 5x to the power of 4, y to the power of 5, z to the power of 9, all to the power of 0. So because everything in the bracket is to the power of 0, this works out to 1. So it doesn't matter what has the exponent of 0, it always equals 1. For number 2, we want to simplify the following as a positive power and then evaluate. So the first one, keeping it fairly simple, 4 to the power of negative 3. We talked about to turn it to a positive exponent, we have to flip it, and the exponent now becomes positive. We don't like to have decimals when we're evaluating this, but we can do 4 to the power of 3 on our own. So this becomes 1 over 64. For b, we have a fraction to a negative exponent, and we talked about when we have a fraction, we flip our fraction, and the exponent becomes positive. To solve this, that power of 6 applies to both parts. So 3 to the power of 6 over 5 to the power of 6. And I can solve these individually. 729 over 5 to the power of 6, which is 15,625. So that is the evaluation. For C, I have a couple of things first that I have to do. I have to use some of my power laws to simplify this. So 5 to the power of 3 times 5 to the power of 4. When I'm multiplying powers, I have to add my exponents, so 3 plus 4 over 5 to the power of 12. This works out to 5 to the power of 7 over 5 to the power of 12. And when I am dividing powers with the same base, I subtract. So 7 minus 12, top minus the bottom, I get 5 to the power of negative 5. And bring this up and continue working on it because now I want to turn it into a positive power. So 5 to the power of negative 5, to make it positive, I have to switch, or I have to flip it. So it becomes 1 over 5 to the power of 5. And 5 to the power of 5 I can do on my calculator, so this becomes 1 over 3,125. So that is the final solution. Now we're going to move into looking at coming up with equations to model specific situations. So in number 3, an autographed Crosby hockey jersey was sold for $750. It is expected to go up in value by 15% each year. Write an equation to model this situation. So the key things are, we have our initial amount of $750, and we have the growth rate. So we know our A value is 750, and our R value is 15%, but as a decimal, 0.15. So to write this into an actual equation, go back up. Remember, looking at that first page, the general form was A 1 plus R to the power of X. Y equals 750, 1 plus 0.15 or 1.15 to the power of X. So that's our equation. Because it wants to know how much it's going to be worth in 5 years, Y equals 750, 1.15. X represents the number of years, so to the power of 5. And this just becomes a calculation. If your calculator doesn't let you do things multiple steps at once, please make sure you follow BEDMAS. So do the 1.15 to the power of 5 first, and then multiply by 750, and you should get $1,508.52 is how much it's going to be worth. And just to keep it in perspective, if you tried to do it the other way, or if you kind of mixed up your operations, you would get a number that would not make sense. It would be too high for its worth. So you do have to use some common sense when you're looking at your numbers or your final answers. For 4, the American bald eagle is an endangered species with a current population of 23,800 worldwide. They are estimated to decrease by 4% per year. So right from the equation, it's giving us a percentage and an initial amount. So A equals 23,800, and R equals 4%, which which is 0.04. So plugging this into our equation, our general form, y equals a1 minus r, because it's decreasing, to the power of x. So this becomes y equals 23,800 times 1 minus 0.04, or 0.96, to the power of x. How many eagles will there be in 10 years? So this is telling us that x equals 10. We can plug this into our equation. Again, make sure you're following bed mass if your calculator requires you to do that. And because it's decay as well, make sure you should be getting something smaller. You should be getting 15,823.02, or you could round that to just 15,823, since you can't have 0.02 of a bald eagle. So that's an example of exponential decay. For writing an exponential relation, looking at a table of values, it's going to be a little bit different. So we have to look at the table to help us find the key information. Again, the a value, or we should be using y equals ab to the power of x. A is the initial value, and b is the ratio. So looking at my table, I do see the initial value when x equals 0, or the y-intercept, right here. So the initial value is 100. For the b value, I need to figure out what the ratio is. So I look at my two terms. I only have two terms back to back here, or two values back to back. So I'm doing the second term, so 97.0299, divided by the top term, so bottom divided by the top, and when I do that, I will get my ratio. And I get that the ratio is 0.99. So that means my b value is 0.99. So in my equation will be y equals 100 times 0.99 to the power of x. And I can use that equation now to find my missing values by plugging in the x value into the equation and solving for y. So for example, for the next one, y equals 100 times 0.99 to the power of 1. We get y equals 99. And for the second missing blank, y equals 100 times 0.99 to the power of 25. We get 77.78 as our last blank. So again, that's how we can use the exponential relation, or a table of values, to come up with an exponential relation, and again, how we can use that relation to find other missing values. So again, this was a review of the exponent units. If you want more in-depth explanation, please go back and look at the previous lessons on these concepts.